Hey, welcome. Today, we're going to pull back the curtain on something you use every single day, probably without even thinking about it: how we actually tell computers what to do. We're going to explore the basic logic that lets a simple machine perform these incredibly complex tasks. And it all kicks off with a pretty simple question.
So just imagine for a second, you've got this assistant who's, well, super literal, a computer. How would you tell it to count all the way to 100? I mean, you can't just say, hey, count to 100. No, you have to give it these really precise step-by-step instructions. So what's the smartest way to do that?
The answer isn't to write print 1, then print 2, then print 3, and just keep going. That would be completely exhausting and just super inefficient. The really elegant solution, the secret sauce, is to teach the computer how to repeat itself. And for that, we use this powerful idea called a loop.
So this idea of repetition, it's really the first major tool in our programmer's toolkit. It's the absolute bedrock of automation and getting things done efficiently on a computer. So let's go ahead and build our very first piece of logic using this exact concept.
Okay, so a loop is kind of like an instruction for a factory assembly line. It basically tells the machine, do this one task over and over and over again until I tell you to stop. It's a really simple idea, right? But it's what lets a computer perform millions of operations in the blink of an eye.
Now, what's really fascinating here is how we can break down a bigger task into these tiny, repeatable steps. This is exactly how a computer thinks. We start at 1, we show it, we add 1 to get to 2, and then, and this is the crucial part, we ask a question. Are we done yet? In this case, is the number more than 10? And as long as the answer is no, we just loop right back to step 2 and do it all over again. And this is what's so cool about this whole idea. By changing just one tiny piece of that instruction, so instead of adding 1, we subtract 1, the computer can now count backwards just as easily. We're using the exact same tool to get a completely different, but totally predictable result.
Amazing. All right, so our program can follow a fixed list of instructions. That's great. But what if we want it to react to us? To do something different based on what we want it to do? Well, that brings us to our next big tool: user interaction.
And this, right here, is a huge shift. Our program goes from being like a pre-recorded message to being part of a live conversation. It can now actually pause, listen for what we have to say, and then act on it. That makes it dynamic and just infinitely more useful.
So how does a program listen? Well, it can ask you for stuff. It can ask you for numbers, like in question 3 from our source material, where you type in 5 different numbers to find their average. Or, like in question 8, it could ask you which number's multiplication table you want to see. Suddenly, the program's behavior is guided by you. You're in the driver's seat. Okay, we've taught our program to repeat itself, and we've taught it to listen. Now for the really, really cool part: teaching it how to make a choice, how to come to a fork in the road and decide, based on the information it has, which path it should take. We do this with something called a conditional. You've probably heard of the most famous one, the if-then-else statement. It's simple. If a certain thing is true, then do this one action. Else, do a different action. This basic structure, believe it or not, is the foundation of all digital decision-making, from checking your password to how complex AI works. All right, let's put it to the test. Here's a number, 13. And here's the big question we're going to ask our program to answer, based on the logic from question 17 in our source material. Is this number, 13, a prime number? Now here's what you've got to understand. The computer doesn't just know the answer. It has to check. It uses a loop, combined with one of those conditional statements. It asks, okay, if I divide 13 by 2, is there a remainder? Yes? Okay, let's check the next number. And it does this again for 3, and for 4, and for 5, all the way up. It's just following a simple, logical, but exhaustive process. So, after checking every single number and finding no divisors other than 1 and itself, the program's condition is finally met. Its loop is finished, and it arrives at its final decision. The number is, in fact, prime. So now that we have repetition and we have decision-making, we can start combining them. And this is where things get really creative. We can now build patterns that look incredibly complex, but are still based on these very simple, elegant rules. Let's take this star pattern from question 25. The computer starts with a loop that basically says, okay, on my first time through, I want you to print just 1 star. Simple enough, right? Then, on the second run of that main loop,
it triggers another loop inside of it. This is called a nested loop that says, all right, this time prints 2 stars. You see how it's kind of building on itself? And by the time that main loop has run 5 times, that little inner loop has followed its rule each and every time, creating this perfect pyramid. It looks intricate, I know, but it's really just one loop tucked inside another, following one simple rule. Add 1 more star for each line. This same logic applies to creating these beautiful mathematical sequences, like the famous Fibonacci sequence from question 22. The rule here is incredibly simple. Just add the last 2 numbers together to get the next one. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, and on and on. A computer loop can generate this infinite, elegant pattern from one single repeating instruction. So why does any of this matter? Because these simple building blocks, repetition, interaction, and decisions, they aren't just for counting numbers or making star patterns. They are, and I mean this quite literally, everywhere. Think about it. We've built this powerful toolkit in just a few minutes. We have the ability to handle massive amounts of repetition with loops, the intelligence to make decisions with conditionals, and the capacity to react to us through user input. These 3 concepts, they form the foundation of almost every single program you have ever used. So let's just recap that toolkit one more time. We have loops for all those repetitive tasks. We have conditionals for making choices. And when we put them together, when we nest them, we can create real complexity and intelligence from the absolute simplest of rules. From your social media feed to the traffic lights in your city, pretty much everything is running on this exact kind of logic. So the final question, I guess, is for you. Now that you understand the basic toolkit for teaching a computer how to think, what problem would you solve with it?